In another video, I mentioned that the Euler-Lagrange equation is a source of an intriguing category of ODEs that come up when modeling real-world problems. And now what I'd like to do is that I want to dive a bit deeper into that. It is a fact that there are many real-world problems that can be mathematically described by the following minimization problem. So what is our minimization problem? Consider the xy plane. Let me draw the xy plane here. X, y, and fix 2 points. Here we go. The first point with coordinates little a and big A, the x coordinate little a, the y coordinate big A. The second point, x coordinate b, y little b, y coordinate big B. All right, so we have 2 points. Let me actually write the coordinates. So the coordinates here are little b and big B. The coordinates here are little a and big A. And you can imagine infinitely many functions, smooth functions connecting the first point to the second point. Here are some graphs of smooth functions that connect this point to that point, the point with coordinates little a, big A to the point with coordinates little b, big B. This is another smooth function. The straight line is a smooth function. This is another smooth function. There are infinitely many of them, right? So we can imagine the collection of all smooth functions that connecting the first point to the second point. Smooth at this point, think about at least differentiable. Later, I will talk about like a theorem that makes this notion of smoothness more precise. So we can imagine functions, smooth functions connecting the fixed point with coordinates little a, big A to the fixed point with coordinates little b, big B. So these 2 points, the initial point and the end point are given to us, and then we can consider all these different paths that connect the first point to the second point. And the minimization problem that appears a lot is of the following type. Typically, they have the following form. Find among all these functions smooth functions that connect the first point to the end point, the initial point to the end point, find the function y from the interval from a to b to r among all functions that connect the initial point to the end point, among all smooth functions that's satisfying y at little a equals big A and y at little b equals big B, right? So among all the curves, among all the paths, among all the graphs of smooth functions that connect the fixed initial point with coordinates little a, big A to the fixed end point with coordinates little b, big B, among all of these functions, find that particular function that minimizes, again, the initial point and the end point are given to you, and you're considering the collection of functions whose graph connects the initial point to the end point. That minimizes the functional, I'm gonna make a comment about this term functional in a second. The functional this is the name of our functional. I'm going to use brackets, and then I'm going to write the input of the functional I of y of x equals integral from a to b, big F, some expression in terms of x and y prime dx. Here, big F is a given expression in terms of x and y prime. A given expression, a given expression in terms of in terms of x and y prime. For instance, x plus y squared plus y prime squared, or x plus y times y prime. Some expression that involves x and y prime. What this expression is, it depends on the physical phenomenon that we are modeling. So it happens, and I'm gonna explain some of the places that this minimization problem appears very soon. That sometimes when you are modeling real world phenomenon, you will arrive at this minimization problem. I'm gonna explain a little bit more about what's happening here. Let me start with the term functional. My friends, functional in this context means a machine that eats a function and spits out a number. So the functions that you deal with, for example, in calculus 1, they eat a number and spit out a number. A functional is something, here I called my functional I. A functional is something that eats a function and spits out a number. This integral will be a number. When you compute the integral, the output will be a number. So let me write this. Let me write exactly what I said. In this context, functional refers to a machine, to an operator, to a box where the input is a function, the output is a number. Functional refers to a machine that eats a function and spits out a number. So here you can think of your functional as this box. In goes a function. You give the input function, and when you apply the functional to your input function, the functional will spit out a number. A function, a number. In goes a function, out comes a number. That is how you think of a functional. And of course, in the context of the minimization problem, the functionals that above, the minimization problem that I have stated above, the functional that we are dealing with, the way it produces the output number is by taking a certain integral. You give the input function here, and then the functional will calculate this integral for you, which will be a number. That will be your output number. If you give a different input function, you will have a different output number. So now let me go back to our picture. So what is happening? Let me call, for example, this the function, this curve that we have on top, y1 of x. Let me call this linear function that connects the endpoint, the initial point to the endpoint y2 of x. Let me call this third graph that we have y3 of x. So these are three functions that are connecting the initial point to the endpoint. You can use your functional I to attach a number to this curve, to this function. What is that number? So I of y1 of x. No, notice that for the input of a function, I'm using bracket. When I want to denote the input of the functional I'm using a bracket, and then I put the input. The input is y1 of x, is a number, that is the number attached to this curve. What about the other curve? What about y2 of x? Again, you can use our functional and attach a number to this guy. Is another number. Now, what is that number? It depends on this expression f that you have in your functional, which is based on the problem that you're studying. Maybe what this function is attaching to your curve is the length of the curve. Maybe it is something else. But it is attaching a number to each of these curves. Let's do one more. So what about the y3? Again, when you apply your functional to this, you will get another number. So you can apply your functional to each of these curves, and what you will get is a number. Now, what the minimization problem that we are interested in, among all these numbers, we want to find the curve that gives us the smallest number. Not just the three curves that I drew, all the possible smooth curves that you can imagine, graphs of functions that you can imagine. When I say curve in this context, I mean graph of a function that you can imagine connecting the initial point to the end point. We want to find the particular curve that gives us the minimum output number among all the numbers that you are getting. We want the smallest. I want to see which curve gives me the smallest. For instance, just so you know, if this I, assuming that this I was attaching the length of the curve, the length of each curve to the graph, then you would immediately say that, Ali, the curve that gives me the minimum value for I is the straight line. That y2 of x will give me the smallest possible number for I, assuming that I was attaching the length of each curve. And of course, the length of the curve, yes, it can be expressed as an integral of some function in this format. But that is just an example. This I can be more complicated. It's not necessarily the length of the curve. All right, so the claim is that in many situations in real life, when we want to understand what is happening, we need to deal with a minimization problem of this form. We have a functional that is defined in terms of an integral, and among all the input functions, we are interested in that particular input function that gives us the smallest output for this functional. Now, let me also list some of the places, just a few of the places that these kinds of problems appear. The one actually very prominent place that you have to deal with these kinds of minimization problems is the Lagrangian formulation of classical mechanics. So let me write it like this. These kinds of minimization problems, minimization problems. They appear in a variety of places, but they often arise in areas, like, so let me list some of the areas that you have to deal with these types of minimization problems. The Lagrangian formulation of classical mechanics, which is an alternative to the Newtonian formulation of classical mechanics. Folks, remember that in several of the problems that we studied previously, when we wanted to study the motion of an object, we used the Newton's second law. There is an alternative way to arrive at the equations of motion in classical mechanics that is called the Lagrangian formulation. And that Lagrangian formulation is based on a minimization problem of the type that I just showed you, the minimization problem of a functional. In this context, it will be called the action functional. So this is a beautiful topic to learn about, Lagrangian formulation of classical mechanics. Another place, for example, that these types of problems appear is continuum mechanics, kind of a study of, for example, deformation of elastic bodies. Continuum mechanics. Let's say that you have an elastic beam under loading, and you want to understand the amount of deflection. One way to attack the problem is to use this principle in continuum mechanics that the equilibrium configuration of a body, like an elastic beam under vertical loading, corresponds to the state that minimizes the total potential energy. And then the total potential energy will be some sort of functional. So this appears in, for those of you who are interested in structural mechanics, in maybe structural dynamics, in elasticity, in continuum mechanics, again, you will need to deal with at some point with problems like the problems that I described above with these kinds of minimization problems. And also in advanced physics, the many of the theories that we have, they are based on Lagrangian viewpoint. I told you that there is this Lagrangian formation of classical mechanics, but what also we have alternatives to it for more advanced theories in physics, like some field theories, for example, field theories in physics. And the natural approach is the Lagrangian approach, which is based on minimization of some functionals in physics. I have to also mention that, for example, quantum mechanics has a Lagrangian formulation based on minimization of some functional. General relativity has a Lagrangian formulation based on, again, you can solve the problems, you can view what's happening in the theory based on minimization of a certain functional, and so on and so forth. So these are like some of the places that you have to deal with these types of minimization problems. Now, how do we study these minimization problems? As a matter of fact, there is a branch of mathematics, and the main job there is actually understanding these types of minimization problems. Let me tell you what the name of that branch of mathematics is. The branch of mathematics dedicated to studying these kinds of minimization problems, minimization of a functional, like the one I showed you above, these kinds of minimization problems is called, maybe I should have called the optimization problem. So sometimes actually the solution of interest is not necessarily a minimizer, it's just a critical point of the functional. However, this is good enough for our purposes here. It's called the calculus of variations. So this is a term that I strongly recommend that you do a little bit of research about. Google the term, find some resources, gain more information about this branch of mathematics. Calculus of variations. All right. So this is all good, but how is this connected to ODE modeling? We were talking about modeling real-world phenomena with ODEs. Where is the ODE here? And to explain that, how this is connected to differential equations, I have to talk about one of the famous results, one of the key results in the calculus of variation. As soon as I tell you about that results, you said, yes, studying this minimization problem is actually connected to studying a differential equation. So let me tell you about this result from calculus of variation. A famous result in the calculus of variations roughly, I'm gonna actually talk about the precise, one of the precise statements of this result as well. But for now, let me just tell you roughly what it says, and then I will write a theorem as well to tell you a more precise version of what I'm just talking about. Roughly says that a function y of x that minimizes our functional I of y equals integral from a to b of f of x comma y prime dx. This is exactly the functional that I had here on top. The function y that minimizes this quantity must satisfy a certain differential equation called the Euler-Lagrange equation, must satisfy the Euler-Lagrange equation, which is a differential equation, as I will write it in a second. Euler-Lagrange equation associated with the functional I. With the functional I. So every time you want to find a minimizer of this functional, you need to study a differential equation. That differential equation is called the Euler-Lagrange equation associated with our functional. And what is that? I'm going to write it here. Definitely we will do an example. We will get more comfortable with it. But here it is. This is the key result that I'm talking about here. The Euler-Lagrange equation says that if you have a function y that minimizes that functional, that function y will satisfy this differential equation. d dx partial f partial y prime will be equal to partial f partial y. F is this expression that appears inside the integral. This differential equation should be satisfied on the interval from a to b, for x in the interval from a to b. Now, if you're interested in seeing a more precise version of this theorem, I'm going to write at least one precise version of this theorem, but we're going to do an example. We will do an example when you will see how we are using this. The mathematical analysis part of this, where we are very careful about the assumptions, that will not play an important role in the discussion that we want to have next in our example. So here, but just for those of you who are curious, here is one theorem that precisely says what the assumptions are for this result that I just mentioned. Theorem. And again, do a little bit of research if you're interested in this topic. Find there are many good resources for calculus of variations, many good textbooks, many good resources online if you want to learn more about this topic. If a function y of x provides a local mean, this is very similar to the things that you saw in Calculus 1, but in Calculus 1, you were dealing with functions where you're dealing with minimizing a function whose input is a real number, output is a real number. Here in Calculus of Variations, we are dealing with minimizing functionals. The input is function, the output is a number. Provides a local minimum for the functional, I of y, the input of a functional, I put it inside a bracket. I usually, instead of using parentheses, I use a bracket. F of x, comma, y prime dx, where y is in C2. C2 means that it is twice differentiable and the second derivative is continuous. That is the smoothness part. At least one version to talk about the smoothness was is to assume that it is twice differentiable and the second derivative is continuous. Of course, we can actually use a weaker assumption here as well. But this is one theorem that we have. And y of a is equal to a, y of b is equal to b. Remember, the functions that we are interested in, they go from the fixed initial point with coordinates little a, big A to the fixed endpoint with coordinates little b, big B. We are trying to find the minimum among all those curves, the minimum of I among all those curves. And C2, again, let me remind everyone, C2 means that the C stands for continuous. 2 means that twice differentiable. The first derivative exists, the second derivative exists, the second derivative is also continuous. When y must satisfy the differential equation d dx partial f partial y prime equals partial f partial y on the interval from a to b. This is the differential equation for y, as we will see in our example very soon. So this is what is called Euler-Lagrange equation. Euler-Lagrange equation. This Euler-Lagrange equation, as I mentioned, is the foundation of many important ODEs that come up in real-world problems. And what we want to do next is that we want to look at one of the examples, one concrete example for that we can use the Euler-Lagrange equation to model the problem that we are interested in. Let me show you the statement of the problem. This is actually it's a very interesting problem. It is historically also of significance, and it's called the Brachistochrone problem. So let me actually start the new video to carefully go over this problem. We will solve it together. You will see how Euler-Lagrange equation can be used in order to find an answer to this very interesting problem.